Okay, today we're going to talk about the chi-square goodness of fit test. Um, Part of the chi-square, this is for seeing if multiple things fit. So this is, did I get the right distribution essentially of M&M colors? Um, we could try to do this, but there is no posted distribution for what it is. And they're not even. They're not even close to even. So the test for goodness of fit is essentially testing, does it fit what it's expected to fit? Okay. You can do this with Skittles, and it does usually work out that each of the five colors of Skittles is 20%. That is the expected for Skittles, and I've actually had good luck with it working out. With M&Ms, it's basically a one in a million that multiple times I've tried M&Ms, and it turns out to be about one in a million. So the idea here with graying of America. So the US population by age group in the 80s. This is the same population in 96. And we can see the different percentages. It's probably more important to compare the percentages. So this was census data from 1980. This is a random survey of 500 people from 1996. And so we have this table. This is what we call our 1980s population, is what we call our expected values. Okay. Or that's expected percentages. We need to not do these in percents. We need to do them in actual numbers. So there were 500 in my survey, so I expect 207 from the 0 to 24 group. So we just multiply the percent times the number in our survey, and we get each expected value. The chi-square formula, and you do this for each line in the table, observed minus expected squared over expected. And then you add them all up. So if I do that, I think they have it later on here. Here it is. So here's my observed minus expected squared divided by expected, and I get this. And I get a chi-square value. This is my test statistic. Your test statistic is going to be whatever number you get from your test, whether it's chi-square, whether it's um, Z, whether it's T. You're going to deal with a Poisson distribution coming up, and there's also binomial test statistics. So your test statistic is this value. If we want to actually find, hold on, let me get the chi-square table. Wait, no, what was it here? If we want to find that, we need to look at our chi-square table, or let our let me pause. Okay, so we have a chi-square table. Um, the chi-square table, we had 4 lines of our chi-square, so degrees of freedom is 3. If we look at this chi-square table, our 8.21 gives us a p-value somewhere between 0.05 and 0.25. 8.22. So it's somewhere in there. So we know at the 5% level, we would reject H naught and conclude HA. So what was H naught and HA? Did they actually reference it? Okay, H naught is always for chi-square, and this is the goodness of fit test. We'll do the other one tomorrow, but it's that it fits the distribution, that the actual values fit the expected values. And yes, we do expect some sampling variability, but within sampling variability that they fit. The HA is at least one proportion differs. And if one does, two will in some way, but two, the other ones might fall within chance variation. Okay, so this one we're rejecting H naught. We're concluding that at least one of the proportions is different from my expected proportion. And if we look at them, these percentages, these values are kind of different. Okay. And they are different enough to be significant, not just chance variation. That's the key thing here. This degrees of freedom for the goodness of fit test. There are two chi-square tests. There's independence association and there's goodness of fit, which is sometimes goodness of fit. Degrees of freedom is number of lines minus one. So, doing another one, and we're going to look at this. We're looking at red-eyed fruit flies, and they have dominant red-eyed. So, capital R here is dominant gene R is red eyes, lowercase r for eye color, along with a dominant gene C for straight wing and a lowercase g recessive. So, dominant and recessive genes. You guys know how those work. The predicted would be this. If you look at this table, you count up anything with a dominant R is going to have the capital R. So red-eyed straight wings is 56.25%. Red-eyed curly wings, 18.75. White straight wings, 18.75. White and curly wings, both recessive, is 6.25. So we are taking our H naught is that my actual values fit my expected. At least one of these proportions is incorrect. To run the goodness of fit test, we cannot use proportions. So we ran this test with 200. So we calculate all these numerical expected values. And where is my data? Do they give the data? They don't show the data anywhere but the calculation. So I'm going to show you how to do this on the calculator. So these are important. Those are my values. So I go to my calculator. I do a new, I add a list in spreadsheets. Observed. One oh one 42 49 10. And then I do an expected column. I'm going to double check that those values are correct. Yep. So I've entered my things They look a little different, but this could be within chance variation. This 49 is a little bit off. 112.5 is a little off. The rest of them are kind of close. But the chi-squared tests that at least one of them is different, and different enough to not just be chance variation. Actually, I do not want to do it on the screen. You can, but it gets messy. So I recommend adding a new page, a calculator page, where you will go menu, statistics, stats test. Chi-squared looks like an X, GOF for goodness of fit. I always call them observed and expected. Degrees of freedom here is, again, 3 because I have 4 different cases, or 4 different lines, 4 different possibilities. I hit OK. I get a chi-square of 5.79. I get a p-value of 0.122, meaning there's a 12% chance that this was just chance variation. So I am going to fail to reject H naught or conclude HA. I don't conclude that these are perfectly as expected, but I can't conclude that they're not. And okay, follow-up analysis. We're not going to talk about simulations because you don't have to do them. So follow-up analysis, if you get a chi-square result that is different or significant, sometimes you want to know where the difference is. So it is often done that you'll do 2 sample t-tests between observed and expected for each one and see which one is different. So you probably don't want to just do a whole bunch of 2 sample t-tests because eventually something should be different even if the overall isn't. But if you have a chi-square that says there's different and you need to look into which one is significant or which ones, then you can do some 2 sample t-tests. And we'll get into that more with tomorrow's lesson.